this presentation will be done in English. Yeah. And today I want to take a bit a closer look to debug on Cortex-M. And who developed on Cortex-M already in this room? So who had already something to do with the Cortex-M? Come on, you all love them. So it's a Cortex microcontroller. And we all had those IDEs to develop on those Cortex-M. They are here to help us. They are here to take everything so that we just have to focus on the development of the product. We don't have to take care about how it is exactly made, so how to debug, and so on and so on. Well, do they? So hello, I'm Jeremy. So Jeremy Gallet. I'm from Belgium, very flat and rainy land, with good beer. I'm an embedded engineer since more than 10 years. I worked in France, Germany, now Switzerland, so a bit all around Europe, and worked for Bosch and Air Liquide, some big names, are very small, so that's why I don't listed them here. And most of my time on Cortex-M development, so Cortex-M microcontroller. Today's menu, so no rush tea, I'm afraid, so we're already at. We will first talk about the IDE, so very peacefully, only good vibes about the IDEs that we all love. Then we will go a bit back to school. So in the theory of debugging, so what do we need to debug? So what is it exactly, and so on. Then we look at the difference that we have. So when we need to debug on Cortex, so actually on microcontrollers, especially on Cortex-M. And at the end, that's why I got here one toolboard. So we will go with the practice directly. We'll do some tests on the board directly because I want to show that it works. So the IDEs. What and I do the most about IDEs? Is there any bad experiences with IDEs? Huh? For example, we have the IDEs, it should work, but like we have debugger not found. Like, so come on, so it just plugged, so it should work. Like, so why is it debugger not found? Sometimes, so for example, the Eclipse-based IDEs, yeah, the story of workspace. We have only open one workspace at a time. And sometimes with the folders, you're like, so yeah, but I open this folder and it's a workspace. It's not like, so I still don't understand how it works. And at the end, I make some change and then I lose some source code. I'm like, so, ugh. And if it doesn't work, then nothing works because it's your only way to debug and to develop on your target. So it's like a single point of failure. Like, so you make yourself dependent of the IDE so that if it works or not. We had also some other experience which are very funny. So, for example, it was the last E-days. I don't know if some with me with the team, we had to develop on the smallest Cortex-M from Texas Instruments, and we had like a strange problem with the IDE. We're like, so okay, so and one of us find, you have to put this file and it works. Like, so okay, why not? And like, it was a bit frustrating and strange, so that we couldn't understand how it worked, but at some point it was working. And another example is like, so here's a screenshot. I started, so STM-Cube here, STM-Cube IDE. It runs idle, no specific, crypto money mining or something like that. But look, 1.6 gigabyte of RAM, like so. And like, so maybe, almost the half of one of the processor, a GPU started, like so. It's a bit like, so what is happening right now? Well, so why do we have like, so all the things working this way? And they're here to support us, to help us. But like, so when you have all these problems and you have to debug, the debugger, I really felt like, like Obi-Wan Kenobi. So he's here to, the IDEs are here to destroy the bugs, not to join them. And so after long years of a misfortunate relationship with those IDEs, I decided it was time to go on a couple therapy and to look a little bit, so to deepen my knowledge, understand a bit more. So end up hoping so that we'll be faster and efficienter. So when I worked on the Cortex-M with the IDEs. But when you go on a couple therapy, It's not always solutions that arise. Sometimes it's questions. And for me, so at the end, I was like, so I discovered a lot. I really found some very interesting things about the IDEs. What do they do when you go a little bit deeper in how they do work? And actually, so you don't need them. You don't need IDEs to develop. Yeah, so you can, with very few things, like maybe 1% of what's in the IDEs, you can put a really fully development environment. And the huge advantage with that, when you keep only the smallest things that you need, as you require, the rest you can do it as you want. You can take your own text editor, for example. Yeah, another thing. So the text editor, I'm a little bit like maybe a maniac, but I like my own text editor. I like some Notepad++, some other like VI or Nano, so some developed with Emacs way much faster than me. So I want to give you back the thing that you could make your own development environment, which means when you go a new target, when you go a new product, when you go a new client, you can still have your environment that you know. That you're like, so okay, I know to put this, I know to do that, and I can be quick and efficient in my work. So everything all right? So do you agree a little bit? Not at all? Because then we will go on a bit of, actually not a little bit, we will go on a theory. You know him, no? We all used it at school, in study, when you had to debug the seg fault. Like, so, wow, where does it come from, this seg fault? The GNU debugger, a very powerful, still used debugger. It works like for C, C++, for Tango, some other languages. It's very efficient. It's used all around the globe in many industries. For us in our private project, we use it a lot. What does it do? Actually, it's very simple. It provides a C environment in which it will run the program. And the advantage of that is that you run your program with GDB, and you will look at everything that happens. You can expose the memory, you can stop the code, you can run the code, you can catch some core files, which means when you have a real, huge problem, you can do a backtrace and look at what happened, which function literally is guilty actually in the problem. And all of that, so it runs in the PC. So when we're at school, we have our first example of program, and then we have the good segmentation fault. We run it on the Linux, and then we start, and then we have the problem. So, which means we have an operating system which provides the whole environment, and we have access to all of it. Now, on the microcontroller, it's here, GDB is here. So I wrote no screen, no keyboard, no hard drive file system. Sometimes you have bigger targets which have that, but still on the small microcontroller, most of the time you have nothing. And you still have to be to GDB here working on your laptop because you want to debug from here. So how do we do that? How do we put a program on the target? How do we run it? How do we debug it? Well, there's two parts, just two parts. First one is a debugger. You all know that. You always also plug your debugger with a USB cable very cleanly so that you hope that the IDE found the debugger. And this debugger has a role to adapt the signal to the target. You have sometimes some different voltage levels. You have different interface. For example, you can use serial wire debug. You can use JTAG. You can trace is a little bit something else. But the debugger has a role to manipulate the target. It can stop it. It can run it. It can flash and so on and so on. Then you have a second part, the GDB-server. Maybe less of you heard about the GDB-server. But this part is very powerful and very important because actually it knows how the target is made. GDB, it doesn't know how the target is made. It just knows how to put a breakpoint, how to run a program, how to stop it, and so on. But in which part of the memory, so does he have to do the flash and so on and so on? How do he manipulate the target? GDB doesn't know, but GDB server, he does. That's why when you start GDB server, you have to tell him, I want to go on this interface and I want to run on this target. And GDB will actually act as a converter, so it will convert. So with those two, we can load our program, we can start or debug, and we can have fun. So fun, depends. here are some example of technical solution. ST-Link server, maybe you never heard of it, but it actually works when you are using ST-Link. ST-Link, maybe all of you worked on an STM target. You use the ST-Link, sometimes integrate it on the target. For example, in this one, I don't know if you see, but yeah, the problem with it's very sensible. So I won't touch it, but if you can see, yeah, there is a small part here, which is the ST-Link. Others that you may know is G-Link and G-Trace from Sega, very powerful, expensive one. You have some cheaper one, but yeah, for example, you can they cost like 800 or 1,000 more francs, depends on features you have. The mother god of them all, the Lauterbach, so very powerful. So you have gigabyte of bandwidth. You can debug on multi-core target and so on and so on. I used it at Bosch. It's complex to understand at the beginning, but it's very powerful. A new one, Raspberry Debug Probe. Raspberry has been surely a lot of use on now. So it's that they made some small microcontrollers, the RP, so 2040 and 2350. Which are very good, so they cost like nothing, like 5 francs, and you have a dual Cortex-M 33 or dual Cortex-M 0 Plus. One that maybe you don't know at all, fully open source, very powerful, Blackmagic Probe. So that's here for the debugger. So gdb-server, you have so the ST-Link server, as I said, you have the ST-Util, which is actually not from microelectronic, but it's an open source one, and it works only with ST-Link. G-Link remote server and G-Link gdb-server command line exe, which works with G-Link trace. And you have the last one. Maybe all of you saw the name sometimes, or what's that? OpenOCD, made by a single guy at the beginning in Germany. Sorry, I forgot his name, but it's a very powerful one, and it works almost on all targets. We have 2 targets that I brought today. An STM32H7 and an STM32F4, which means we have a Cortex-M7 and a Cortex-M4, sorry, and German sometimes a bit mix. So that's our 2 targets, and the aim is to run a ThreadX real-time OS on it, and we will use the GNU-arm toolchain for that. Any questions? Any things unclear? Otherwise, I will start. Here we will go on the first test, and I think that my Raspberry just made some special movement. Yeah. Okay. I think sadly I lost my target. That's very good. So we will restart it. That's why we had some technical problem at the beginning. So deeply sorry about that. Very good. ESL. I hope you work. No. Very good. Whew. So now this one works. Exactly. So as you can see, we will have to run a couple of programs and time. Yep. So the first one will be to plug the debugger. So the debugger is plugged, and then we will have to connect the debugger with the GDB server. From that, I'm going to an example project, so H7, and I have my binary file here with. Does everybody see enough? Is it good? So with the view, I have an ELF files. It's files that contain all the debug symbols. And to start to debug, I can. So I will start to run actually a GDB server, and for that, I will do open OCD, and I can give it a config file that's actually just here. Config, and yeah, I have to say use this config file, and here it detects my target. So GDB server just locked. My target here is blocked. I can start from another one to debug. So which means here, if I go in the binary, I do arm node-rb gdb, and I tell him to put use this debug file. Then I go to my my GDB is not yet connected to GDB server, and I have to connect it. So I tell him target, extended remote on localhost 3333. As you can see here, you have the starting GDB server on the ports that you have to connect to. Right now I'm on localhost, but you can do it remote as you want. As you can see here, GDB server said, hey, I'm ready. So what do you want to do? Load my target. Please load the program. Now it's ready. So I flashed my target, can do run. Do you want to start the program at the beginning? Yes. Now it starts the program, and now you're okay, wow, as we can see, we see a lot of things. Now what's very powerful is that I can do Control-C, block my target, and I can start, for example, to look where I am in the code with list. Okay, here I am. I can print the backtrace. I can print, for example, I don't know, thread input. What is it, thread input? So I say print me as an hexadecimal thread input. This is 0.0. Okay, super. If I tell him print me the address, it print me the address, and so on and so on. You can do step to continue it a bit, so step, carry on, or you can do okay, continue your work. Here you can debug like as you want. So there is a lot of other, all the command lines that you find on the IDE, you find them here in the command line. So there is a lot of more command lines that you can do. I'm pretty sure I forgot some of them to show, but you can do that afterwards. So,
Jeremy,
what will be also interesting? Yeah, a very good thing to do is here I showed you have to connect, you have to load, blah 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 blah. You're okay, but now with IDE I just make a click and it works. Like here, so GDB is smart. You can actually put a script file so that when you start GDB, it will automatically connect, load, and be ready. And if I do quit, yes, I have a point GDB init file. And here we can see the different commands that I made. So target extended remote, you will connect to the target extended remote. Then it will load, and it will do two good things so that I can debug it a bit better, so look at the variable a bit more, and so on and so on. So set print pretty is just that it will print me beautifully with all the name, with all the values, all the pointer. When I look at big structures, so variable, for example, it will print it beautifully. Which means now, actually I could do an alias. I already prepared them, and which means, for example, I have a GDB here, which means run GDB, take this GDB init file, and please load my ELF file. So it means if I run a GDB, connect, load, ready. Which means now with just two command lines, I just replace the other IDEs. You don't need any IDEs here. You can modify as you want. I would gladly do it, but I'm a little bit afraid of moving this computer right now, but I can go like in the floor and I will still have the connection in internet over my Raspberry Pi here. And for example, it could be at Ibiza or something like that and still carry on to debug, which is nice. In the sun, we like it. Exactly. Now, so to recapitulate, bit of the chance. I hope I don't step on the what we made. So we had our target. We connected the debugger, which is already connected. We started the GDB server in the first terminal. We run GDB and we connected to the GDB server. And now there is one last thing I could show you, which is to put actually to the serial communication also to read it. So it's a bit, you don't need any GDB for something like that, but it's very useful. Some debugger propose a virtual COM port. And actually, for example, ST-Link, it has here, so directly inside of it, so serial communication on a default UART port, which means all the printf, all the log communication you want to have in your target, you can forward them directly with Minicom, so to serial, and read them with Minicom. So if it works, for example, sometimes, and I do, yeah. Let's show that a little bit. No, you want it to show. So in 3 terminals, like a fully development environment, if I do dev tty, we can see here a beautiful device. And so just to know, so ACM means so ARM Cortex-M. Very useful, so acronym to know, so that I discovered like a little bit later, but it's very useful. And I can do like Minicom on a device /dev tty ACM 0. It's ready. Here I can do run. Yes, up. I see my message. I see the thing working. So here, 3 terminal, full development environment. Now let's look a little bit also at something that's very funny. I go here. I hope it will divide. Well, not this one, but like I wanted. Check. If I do now, connection again, and I do it htop. Here is like the percentage of CPU I use. I have a really cheap Raspberry Pi. Actually, I use 0.1% of my memory. So it's not like the big STM32 IDE that use a lot. Actually, I have a full development environment, and it costs me nothing on my target. I can use a very cheap computer and still be able to work. Okay, I will stop it here. Tick. And go back because give it time. Still good. Wrong button. Now, other targets. I want to show you that the step that I made now, it's the same for every Cortex-M target. You still have to connect to the serial wire debug, plug your debugger, start GDB server, if any, and then you're ready to play. Here's the combination I made. I tested. All the time I had except like sadly I didn't still made it, but like so for the last Raspberry microcontroller, I didn't put the ThreadX, but for all the other one, I put a ThreadX. I have examples of project, and I could with all those debuggers, I could select the one I want, and it still worked. It was still the same environment. It was still the same step. So which means if, for example, a colleague is using the big debugger and the only one for the 5 people of the team, I can still take one. I can find a solution. I can still be able to work. I'm still I don't have to wait for the other to give me the debugger. Another advantage is that you don't have to buy 5 debuggers, which cost like, I don't know, 1,000 franc for the whole team. And if one debugger doesn't work, just use the other one. One I could really want to show to you is the Blackmagic probe, because it's open source. You can You have all the documentation accessible on the internet. You can actually also take the PCB, do it yourself. You can also take the source code and flash it on an old STM4 Nucleo board and use the Nucleo board actually as a debugger. It's possible. They explain how to do that. And another advantage is that it has an integrated GDB server, which means you don't have to start a GDB server. Just plug the target as the debugger, and then when you start with GDB, you tell it not to go on the target extended remote, so 33333. You tell it to go directly on the device, the Blackmagic probe. Or do you want to look at another one? I can show you also with G-Link how it works. It's still the same. You have any preferences? Or I go with Blackmagic probe, and then afterwards we can go on other debuggers. So actually it was very funny on this one because it is not meant to have an external debugger, but I found a solution how to put an external debugger on it. So it was like, so sorry, but you will have an external debugger. Now let's go back to our, if I do exit here, yes. Quit, yes. Here I can release the debugger. Here I can do quit, yep. And now, so I have to go on my project F4 because we're on a target. I still have here, so my full development environment, and what I do, I go on binary. I just have to do the ARM Nonabi GDB. Come on. Yeah, G10.elf. Up. It's ready. And now I don't have to start the GDB server as said. I just have to look at the device. And here we see so Blackmagic GDB. So it's very useful. I just have to copy paste it. Actually, it's all the time the same. So you can put it also in a GDB init file, so which will automatize the thing. But like now I go on target. Check. Oh. What was it the command again? I need to, sorry. I have some target extended remote anyway. Target extended remote. I do auto monitor, auto bit scan. You can automatize, I said, all those commands. It tells me, so, hey, I have this target. Do you want to attach it? Yes. Attach the first target. I can do load. It's ready. We can also start the minicom again. Let's smash dev tty. I have here, I know that this one, sorry, I made the test before. Minicom -d tty, and here just run. Up, starting again. And here you have actually no needs of your targets. So because the GDB server is working on this small piece here. Everything works. One thing that's very useful also with GDB this way is that you can actually recompile your target directly from GDB. You don't have to quit. It means if you made some breakpoints, if you had like a specific development, debug environment, you don't have to quit, restart, reload, and so on. You can just remake your program directly from here, which is quite useful. Okay. The time should be good. Maybe I will take back the delay we had. As we can see, we see nothing. It also want to go on a break. The computer. Oh yeah, we're back. Before I go to the conclusion, is there any questions? Actually, we will have question time afterwards. So back to the title. Is it cheap? So I must say quite cheap because ST-Link, it costs like 80 francs. The Blackmagic Debug Probe, you have it for free if you want. You can buy a finished, so all fertig. So I don't know the word in German, sorry, in English, sorry. But you can buy once on the internet. It costs also like 80 francs. Yeah, so they're not that very so expensive. You need way much less resources on your computer. Here I developed a Raspberry Pi. It costs like 100 francs, very cheap. You can reuse the old debugger, so the also evaluation board, like the Nucleo board. So I say it's quite cheap, easy, also quite. As I showed, like with a couple of command line, you don't need any IDEs. Also, there is a very powerful way. So it's very powerful to do it this way, in my opinion, because you have a good control about what is happening. You have actually all the features that you have in the IDE to step, run, debug, and so on. You have it all. And also something that's very important, in my opinion, it's also not only cheap and easy, it's also flexible. You can tailor it the way you want. You can do it also, you can easily debug from remote. You can put your own text editor. For example, I work also with Nanos, like it's old school, I like it. So it's actually more than that, not using the IDE. Another conclusion is like, so is it for fun only? Because like, yeah, you're working like, here you made some with cheap debuggers and so on. For me, it's not just for fun. OpenOCD is actually what is used in the STM-Cube IDE. It is used in a lot of others IDE. If you look a bit, you can invite you to open the files when you download. So if you have STM-Cube, go a little bit in the files, in the plugin, you will find an OpenOCD, a standalone OpenOCD. So it's like, so, okay, actually, I can work myself with OpenOCD. And when you start a debug session, it will start OpenOCD for you. GDB, yeah, it was there. So maybe before I was born, it will be there surely after I'm dead. So it's very powerful. It's still used. So even if it's so for free. And there are very consequent projects from open source community. For example, the Blackmagic Probe, which works perfectly. To have the integrated GDB-server is like, so just plug and play and run and have fun. Some drawbacks, so you have to find the good OpenOCD script. I had to search a little bit, so but then as soon as you have it, as you know how you have to configure it, then it's piece of cake. For example, I've worked at the beginning on the STM32H7, and it took me, so I had 2 weeks of work, and then it took me only 1/2 a day to migrate all the development environment for STM4. Just had to tell OpenOCD, don't go to the STM32H7 script, but on the STM32 F4 script, and that's it. It's not official, so which means so you won't have the support if something doesn't work, but sometimes we all know that. You call the support like, say, yeah, we're working on it, and then 3 weeks later, so still working on it. What's next? So if it pleased you, that's my email address. Please send me an email. So tell me if you want to have more information. I made 4 examples of projects with a single CMake list file with how do you integrate the ThreadX real-time OS? How do you integrate the different source code from STM-Cube? So from the STM32 HAL, so hardware abstraction layer. Also, I did it for 2 other projects that I didn't show today, but for the RP2040 and RP2350. Yeah, and I also wrote a huge amount of Markdown, so how to understand how OpenOCD works, where did I found the different scripts, so how can you do it yourself to find the different scripts. What's next? I want to do it on the other families of microcontrollers, the NXP, Microchip, and TI. So also proposing Cortex-M development environment, and I want to hack them. I wanted to go on the tracing because it's possible also to have open source device to do tracing. Tracing means you can do code coverage, you can do code analysis, you can analyze the code efficiency. There is a powerful project, Orbuculum, which proposed to do it with an FTDI. I like, so okay, so because these chips here cost only 20 francs, which means if you can do tracing we all know, so like tracing, like so you have to buy a big guy, like so buy a debugger, which costs like 2,000. So like so I don't know what I'm doing. Like this, it looks like it works. Actually, you can do it with an FTDI. So normally, I want to try to test it. Tracing also with serial wire only, so a serial wire output. It's proposed by the Blackmagic probe. It has a pin, so you can do a slow, but still have the possibility to do some code analysis with this single pin. To go on the RISC-V architecture, so that we can also propose, hey, here is how you have a very simple and clean development environment for RISC-V architecture, and also to explore a bit more multi-core debug, because it's a bit more complex, to show, so how do you stop a core if you can do it, if you can do it parallel, so and so on and so on. Thanks a lot. I hope you're pleased that no nuclear board nor artificial intelligence were hurt in the making of this presentation. And I want to thank a lot of friends who helped me in the making of the presentation, especially Melchior Glattard, who is a trainer in rhetoric, and he helped me a lot to put, I hope, the good words that you understood a lot today.